Hello, and welcome to the podcast that explores the connections between engineering, technology, humanities, and the arts. I'm Jeff, and today we're talking about how a small blue bird redesigned one of the fastest trains in the world, the story of the Kingfisher and the Shinkansen. In this episode, I'll walk you through the story in three parts. First, the problem. Why Japan's 500 series Shinkansen produced a loud boom every time it exited a tunnel. Second, the discovery. How an engineer who was also a bird watcher found the answer in the beak of a kingfisher. And third, what happened once nature's design was tested and put into service. Along the way, we'll see why this became one of the most famous examples of biomimicry in engineering. Let's start with the problem. In the 1990s, J.R. West was developing the 500 series Shinkansen to run at 300 kilometers per hour. But there was a catch. When the train entered a narrow tunnel at high speed, it compressed the air in front of it like a piston pushing through a tube. That pressure wave raced ahead of the train and burst out of the tunnel exit as a loud boom, disturbing residents up to 400 meters away and violating Japan's strict noise regulations. Something had to change, and it had to change without slowing the train down. The lead engineer on the project, Eiji Nakatsu, happened to be an avid birdwatcher. He realized the train's problem was really a question of moving smoothly between the two mediums, from open air into the compressed air of a tunnel. And that's when he thought of the kingfisher, a bird that dives from air into water, a much denser medium with barely a splash. The secret is its long, narrow, wedge-shaped beak, which lets water flow past instead of piling up in front of it. It's a shape that took millions of years of evolution to perfect. Also, the bird can catch fish without losing speed or alerting its prey. But the team didn't just copy the shape of the beak and hope for the best. They tested a whole series of nose designs, from blunt to increasingly slender profiles, using shooting tests that fired scale models into a pipe to simulate entering a tunnel, along with wind tunnel testing and computer simulations. The data consistently showed that the shape closest to the kingfisher's beak produced the smallest pressure wave. The final design was a nose about 50 meters long with a nearly round cross-section, strikingly similar to the bird's profile. It's worth noting that this wasn't a quick fix either. The redesign process took years of iteration before the team landed on a shape they were confident that would work at full scale. The redesigned 500 series entered service in 1997, and the results went beyond just solving the noise problem. The train met the 70 decibel noise standard, used about 15% less electricity, and traveled about 10% faster than its predecessor. And the kingfisher wasn't the only bird involved. The pantograph, the arm that collects electricity from overhead wires, borrowed the serrated edge of an owl's flight feathers to cut down on wind noise, since owls rely on silent flight to hunt. This project is now a textbook case of biomimicry. Instead of forcing a solution through brute engineering, the team asked a different question. How had nature already solved this exact problem? And it turned out nature had been perfecting the answer for millions of years, waiting for someone to notice. Today, we covered how the kingfisher's beak inspired the nose of the 500 series Shinkansen, turning a noise problem into a faster, more efficient train. To me, The biggest lesson here is that good engineering starts with careful observation, and sometimes the best design manual is the natural world itself. Thanks for listening.